Welcome to LIB Academy. In this video, I'm going to take you through the second shifting theorem and the Laplace transforms. Well, we are not going to prove the formula here, but I'll just write it, and we'll start working examples. You can check a video for proving, a video that I prove the formulas out. Yes, so you can check that video out for the provings. Well, a quick revision on the first shifting theorem. For the first shifting theorem, we dealt with, let's say, if we have an exponential function e to the power t multiplying a function f of t, in which that function it can be a cos function, or a cosine function or sine function, right? Then we say that for that one, where we just write the Laplace transform for the second function, the f of t, and then wherever we see s, we replace it by s minus a. For instance, e to the power et multiplying sine omega t should give us, we just find the Laplace transform for this. We know that the Laplace transform for this is just sine function, so omega over s square. So since we have s here, we replace s by s minus a all squared. It was supposed to be s square, right? So plus omega square. So that is just a hint about the first shifting theorem. Well, if you don't understand, let's just keep it for now and deal with the second shifting theorem. So for the second shifting theorem, it turns out that we will have a function, and that function is not e to the power at, even if we have it, but it will contain a term, let's say t to the power n. So we can have t to the power n multiplying e to the power at and sine omega t. So how do we solve those problems? So that is what brought, that's what led us to the treatment of the second shifting theorem. So without wasting much time, this is the basic definition for the second shifting theorem. So Laplace transform of the function 2 to the power n f of t equal minus 1 to the power n d to the power n over the s to the power n. This is just a very simple thing. Take your time, I'll explain it to you for easy understanding. So in this case, our f of s here is a Laplace transform for f of t, right? And this n here is what is coming from the t term, right? This t here is just an algebra, right? It can be x to the power something, m to the power, just a variable. And the power is what we are looking at, and we are calling it n, right? So now we are going to take a typical example. So that is just the second shift theorem. So this is just a formula, and by the end of this video, you know how to work with this problem. So our f of t here can be cosine, can be sine, can be exponential, right? Exponential, it doesn't matter. So let's take our first example. Find the Laplace transform. The symbol here indicates Laplace transform of t sine t. And now, looking at this, you can see that there is a shift, and this shift is typically the second shift theorem, because you are not seeing a term like e to the power at, generally e to the power at sine something, but rather seeing an algebraic value multiplying sine t. So in this case, we know that comparing to this formula, this is t to the power n here, and we can spot our n out, and our f of t, this is our f of t. So, and the general formula is that the Laplace transform for this, it should be equal to minus 1 to the power n d to the power n over ds to the power n f of s. And f of s is the Laplace transform of f of t. So firstly, we have to look out for our f of t. This is our f of t. So our f of t now equal sine t, right? And now let's look out for the Laplace transform of f of t. Laplace transform of f of t is, since sine t is our f of t, is just sine t. What is the Laplace transform for sine at? This is actually at. Our a is here because our a is not more than 1, then there's no need to write it. If it were to be more than 1, you could have seen 2 here, 3 here, or something here. So for sine function, looking at our basic Laplace transforms, sine at equal a over sine square plus a squared, right? We need to know all these things. So sine at equal a, and our a here is 1, right? Which is 1 over s squared a squared. So s squared and a is 1. 1 squared is just 1, right? So now we've gotten this. Since our f of s is the Laplace transform of f of t, and our f of t is sine t, so now we've gotten our f of s. So our f of s now equal 1 over s squared plus 1. So now the Laplace transform of this L, Laplace transform of t sine n t, sine t, should be equal to minus 1 to the power n. And what is our n value? N is coming from t, the power of t. Even if it's not t, if it is any variable at all, that power, its power is n. So since n is 1, we have 1 here. Dn over the Sn. So d to the power n, there's no need to write it. So s to the power n, there's no need to write. So in our f of s, we calculated our f of s. We know that our f of s is the Laplace transform of f of t. And from the question, we know that f of t is just the function in front of the t, right? Or either the function, any function here apart from t, and it is sine t. And we were able to find the Laplace transform of f of t, which is sine t, and gotten it to be 1 over s squared plus 1, and that is our f of s. So Laplace transform for f of t is f of s. So now we have our f of s here to be 1 on s squared plus 1. So what this means is that we are taking the derivative of this term. We are to differentiate this term. Let's say our n was to be 2, then we are going to have 2 here and 2 here, meaning we are going to differentiate this whole thing twice and multiply it by minus 1 to the power n. If it is 2, then like minus 1 to the power n. So now let's look out for the differential of this. Let's differentiate 1 over s squared plus 1. So differentiating 1 over s squared plus 1, I would like to use the chain rule, which is more sweet. So I'll find a way of sending it up. So this one is just the same inverse of this. So is just writing this as plus 1 e to the power negative 1, right? So using the chain rule, we multiply everything, the power by everything. Just bring the power minus 1, then you write everything s squared plus 1, and the power is going to decrease by 1. There's already minus 1 there, and the power will decrease by minus 1 again, right? So we multiply everything by the differential of what is inside. So differentiating s squared 2 by s, and differentiating 1 is a constant, just gives us a 0. So this whole thing is going to be minus 2s multiplying s squared plus 1 to the power minus 2. Then I'm done. So I can just bring this one to its original place. So this is going to give me minus 2s all on s squared plus 1 to the power positive 2. So now this is just my differentiation. So I've gotten this side now to be 2s minus 2s. My minus 1 is already there, multiplying minus 2s all on s squared plus 1 all squared. So at the end of the day, we are going to see that we have minus 1 multiplying minus of this. So this is just going to give us positive, which is 2s all on s squared plus 1 all squared. So this is our final answer for this problem. The problems comes in for the differential. Like if you have your n to be more than 2 or more than up to 5, then it means you are going to differentiate this whole thing here 5 times. And there's a need to know Leibniz rule. So you can check my other video out. If we are to treat Leibniz here, then it's somehow going to make our video long. So let's continue with that second example. Find the Laplace transform of t sine 2t. Like you seeing this, you just know that we are dealing with the second shifting theorem, right? Good. So now we know that for the second shifting theorem, the Laplace transform of t sine 2t to give us minus 1 to the power n dn over dsn f of s, where f of s is the Laplace transform of f of t. Let's say any function here apart from that t. So now what we are going to do is that we know the value for n. Yeah, n is 1. N is the power of t, 1, right? So which means we can just say n to the power 1 is just minus 1. So n to the power d to the power 1 is just d all over ds f of s, right? So now let's look at for our f of s. So our f of s, which is the Laplace transform of f of t, the function apart from t. So we are going to find our f of s, which is called Laplace transform of this function right here. So sine 2t, right? Sine 2t, right? So this is a sine function, and we should know the basic identity that relates sine function. The basic one is e over s squared plus a squared, right? So that's it. And now we know the value for our a. Our a here is 2. So a, which is 2 over s squared, which is s squared, plus a squared, 2 squared, which is 4, right? Good. So now we're able to know what our f of s is. So we can go ahead and substitute it into our expression. So d over ds s squared plus 4. And I told you that this means that we are going to differentiate this one. We are going to find the first derivative of this. since we are having s to the power 1, d to the power 1. If it to be d to the power 5, s to the power 5, then we have to differentiate this whole thing 5 times. And I'll cover that in my next video. So now, let's take this whole thing here and come and differentiate it. So we are finding the differential of 2 on s squared plus 4. Like I said, I would like to send this out to use the chain rule, which is very sweet. So 2 multiplying s squared plus 4 to the power negative 1, right? So using the chain rule, I'll multiply this. I'll just bring my power, which is minus 1. Then I'll write s squared plus 4. The power is already minus 1, and it will decrease by minus 1 again. Then I'll differentiate what is inside. Notice that all are multiplying. So differentiating s to the power 2 gives me 2s, and differentiating 4 is a constant, so just go away. So this whole is going to be 2 by minus 1 minus 2 multiplying s squared plus 4 to the power minus 2. I'm done. Let me bring it back. So this is going to give me minus 2 all on s squared plus 4 all to the power positive 2. So now this is just my value. So I'm going to get minus 1 multiplying a whole of 2 on s squared plus 4 all to the power squared, right? So since I have negative 1 here multiplying negative 2, I'm just going to get positive 2 all on s squared plus 4 multiplying, all to the power squared. So that is our answer for this question. Let's look at our last example. Find the Laplace transform of t e to the power t sine t. How do we do this? So looking at the general formula, the Laplace transform of t, f of t, should be equal to minus 1 to the power n dn over ds to the power n f of s. So, and f of s here equal to the Laplace transform of f of t. So looking at this question, everything here apart from t is our f of t. So equal to Laplace transform of e to the power t sine t. Right? So we have a shift and a shift. This is from the first shift theorem, where we have exponential function multiplying a sine by multiplying a sine function. So what we just do is that we write the Laplace transform for the sine function, leaving the exponential function. But however we see s in the sine function, we replace it by sine s minus a. To cut everything short, this is what I'm talking about. So we have e to the power something sine something, right? So this is from the first shift theorem. So we have omega or w over sine s minus a to the power 2 plus omega squared, right? So now what we need is the value for a and the value for omega. And omega will come from the sine function, a will come from the exponential function. So from this point, at this point, we know that here the exponent of t is 1, so a equal 1. And here, there's no number here indicating that omega is also 1, right? Good. And our Laplace transform for e to the power at sine omega t equal omega over s minus a squared plus omega squared. So, and this is going to give us, we know the value for a, we know the value for omega. So, omega is 1. So, we are writing 1 here all over s minus a, and our a is also what? 1. So, omega squared, 1 squared is the same as 1. And don't forget to bring in the square here. So the Laplace transform of our f of t, from this function we found that our f of t is this, and that's it. The Laplace transform for our f of t is our f of s, and that is what we are just doing. This is our f of t, this is our f of t right here. So I recommended simplifying the denominator so that when we are doing the differentiation it will be easy. So simplifying this denominator, what I'll have is 1 over square s, then you square s, multiply everything by 2s minus 1, so minus 2s, then you square 1, giving us positive 1 plus 1, giving us 2, right? So this now is equal to our f of s. Mind you, we said our f of s is a Laplace transform of f of t, and we will get f of t from the question given. We just look at t and any other function. Generally, any other function apart from t becomes our f of t. Then we find the Laplace transform of that one. So now let's simplify. Let's substitute our values into the general formula. So now we are going to get, since our n is 1, we are going to get minus 1, just minus 1 d over ds. N is 1, then 1 here, 1 here, so just leave it that. And our f of s is 1 over s squared minus 2s plus 2, right? The next thing we want to do is to find the first derivative of this term right here. So let's go ahead and do that. I want you to know how to work with problems like this so that when we meet in the next video, we'll be looking at derivative, field derivative, fourth derivative with ease using the Leibniz theorem. So I want to find the differential of this. So 1 on s squared minus 2s plus 2, right? Yes, I would like bringing it up so that it will be sweet. I will use the chain rule. So s squared minus 2s plus 2 to the power minus 1. So I just bring my power minus 1 here, and I'll write whatever is here, minus 2s plus 2 minus 1, and this time the power will decrease by 1. Then I'll just differentiate whatever is inside the bracket. So 2s minus 2, right? So that at the end of the day, I'm going to get minus 2s minus 2 s squared minus 2s plus 2 to the power negative 2. So I can just bring it down. I'm done with this, so I can just send it back. 2s minus 2 all on s squared minus 2s plus 2 all to the power 2. As easy as that. So now that I'm able to find the differential of this, so this whole term right here is going to be replaced by this. So I have my minus 1 already there. So multiplying by all of this, which is the differential of everything here. So this is just going to be multiplying minus, wow, okay, minus 2s minus 2 all on s squared minus 2s plus 2 all squared. Now that I have minus here, I think this minus can take care of that minus. So that will just go away. So I'll left with 2s minus 2 all on s squared minus 2s plus 2 all to the power 2. So this is our final answer for a problem like this. Thank you for watching, and see you in my next video where we'll deal with higher derivatives.